Hello, I'm Orion Sauter, and I'm going to be telling you about some work that I've been doing with my colleagues Peter Wass and Henri Inchaspe on the effect of LISA Pathfinder style glitches on simulated LISA TDI data. So first, I want to give you an idea of the system that we're working with here. So this is one of the 3 LISA spacecraft, and inside each, so we've got 2 MOSAs in each one that point to the opposing spacecraft. And inside each MOSA is the electric housing and the test mass. And so in the test mass coordinates, the x-axis points toward the opposing spacecraft, and those are required to be free-falling for the test masses. And then along the other dimensions, they are electromagnetically stabilized by the electric housing. However, stray forces can cause unexpected motion, which was observed on LISA Pathfinder. The LISA Pathfinder collaboration has recently put out a paper that you can find here discussing these glitches. But what we were curious about was how this unexpected motion will affect the time delay interferometry, which are the primary outputs of the LISA constellation. So we have several simulators to assess that because LISA is not yet in orbit. So there's LISA node, which is a full constellation simulation. It's built in Python and then compiled from C++ to create binary. So that currently, although it's being updated now, does not include the dynamics of the test masses and spacecraft. That is implemented in LISA DIN, which is a dynamic simulation based on a MATLAB state space model. That is currently being added to LISA node, though. Then there's the LISA simulation suite, which are pure Python packages that together simulate the constellation. It includes LISA instrument and PyTDI, which are the 2 that we're interested in for this final method called glitchdyne, which is a combination of the LISA DIN control scheme with LISA instrument and PyTDI. So that's what we're going to be using in the data that I analyzed here with the for the glitches. So the glitches that we're using are LISA Pathfinder Shapelet Glitches. This represents a common glitch form seen on LISA Pathfinder. It's implemented in the LISA glitch program, and it has 2 parameters. There is the level, which represents the final delta V imparted to the test mass. And there is beta, which is a time constant that represents the time that the max acceleration is imparted to the test mass. So these 2 parameters have a range of values that were seen on LISA Pathfinder, and we explored that full range. So here is what the glitches look like in acceleration. This is the test mass acceleration in meters per second squared. So at the beginning of the glitch, there's a quick kick of acceleration that reaches this maximum given by, well, so the A is the change in velocity. So this maximum acceleration is at the time beta. And then there's a long exponential tail off as that force is decreased. If we carry these through to TDI, in this case, this is TDI X, you can see that we get this pulse, sort of a rounded pulse in the TDI. And one interesting thing to note here is that even though the second glitch in orange has the higher amplitude, because of the longer beta, it's more spread out. And so it has less of a total effect on the TDI. So something to note for a little bit. So now how are we going to detect these glitches? So nominally, the TDI data is just Gaussian noise with constant mean and standard deviation. But as I just showed, the shapelet glitch results in a rounded step shift in the test mass velocity, which is a rounded square or a rounded pulse in TDI. For small betas, this gets turned into a square pulse as it hits a limiting factor. So we can compute the log likelihood ratio using a Gaussian likelihood with the data minus the proposed glitch TDI. So for the null hypothesis, we have just the data put into the standard Gaussian likelihood formula with the maximum likelihood formulas maximum likelihood parameters calculated in the standard way. And then the other option is we have the data minus the glitch as the alternative hypothesis. And then for the likelihood ratio, we do log likelihood ratio, we do L1 minus L0. And so, in theory, any positive values mean that the glitch is more favored than the no glitch. All right. So to test this, we created a grid of log level and log beta values, each with a random test mass injection point. So there are the 6 test masses, so we just choose one at random to inject the glitch on. And then we generate the TDI using glitchdin. And the results that we get have been checked against LISA instrument and Pi TDI without the dynamics, and they are consistent. So then we calculate the log likelihood ratio for the template of matching parameters. So for now, we're just exactly matching what the injected glitch. But we vary the glitch start time so that we can see where that maximum likelihood occurs. And so then we can compare the true injection time versus the time predicted by the max likelihood. So first, before I get to the times, I just wanted to show the type of log likelihood ratio values that we get. So you can see here that, so this is showing for the different level values that we tried. You can see that to get away from 0, we really need to be at the extreme high end of the levels. So it's really only the more powerful glitches that we can see. And then over here for beta, it's really interesting to note that this beta has a peak in likelihood around the 10-second value, while for incredibly high beta values, it tapers off to 0 again. And so that's the effect that I was pointing out earlier, where longer betas lead to less effect in TDI. We can also plot this in 2D to see this sort of bulge that we get, again, at the extreme levels, but moderate beta. All right. So then also of interest is measuring how long the disturbance in TDI lasts. So for that, what we did is we calculate the likelihood for a subset of the data that is consistent with Gaussian noise. So we take a point in the data, and then for that point to the end, we check the likelihood of Gaussian distribution. And so then we can find the time where the value is within 99% of the maximum. So you can see here in this plot, this is showing that likelihood from this time to the end of Gaussian distribution. And so then this point is where it hits that 99% maximum value. And you can see that it does seem like a reasonable measure of the duration of this TDI disturbance. If we plot those total durations against the betas, we get a power law relationship, except at the very low levels of beta, where I mentioned the squaring off that we get when we sort of hit those lower values. And then we can estimate the glitch time. So as I mentioned earlier, we're moving the glitch around against the data to see where the optimum subtraction happens. So for if we just are looking at all of the values that we got, it goes anywhere from the extreme negative to thousands of seconds away. But if we place the cut of the log likelihood greater than 0, so this is the likelihood ratio again, so that greater than 0 means that the glitch is more favored than no glitch. But with just taking that cut above 0, we're still getting a lot of values that are very far off. But then with just a small cut of greater than 1 rather than greater than 0, we get all the values are right around 0. So that seems very promising for the ability to estimate the true glitch time. So the next steps that we're planning to take, if we can detect these glitches, we can filter them before performing a search for signals that can improve our sensitivity. But we need to know how accurate we need to be to get these parameters for good subtraction. If we're a little bit off in beta or level, how much does that hurt us? And then also we need to know, well, how much does that really improve our detection capability? Are these glitches really going to be a major obstacle that we need to subtract? So the Spritz data challenge that is part of the LISA data challenge includes shapelet glitches. And so that's a good test case for this detection and subtraction method. So we're going to be looking into that in the future. And we are in the process of adapting this technique to cluster use for greater resources. Thanks for listening. And if you have any questions or want to discuss anything with me further, you can reach me at this email address. Thanks.